Here's the recap video for wave properties. Most of the time we'll be dealing with sinusoidal waves, so we know that for the velocity of a wave v, it's equal to the frequency multiplied by the wavelength. We can think of this as a rearrangement of the equation d equals vt. Solving for v is d divided by t, distance over time, and the 1 over time is the frequency. So frequency times wavelength is velocity. As shown in edX, we can rewrite this as the ratio of two quantities, omega and k. Omega is some quantity that we are quite familiar with. It's 2 pi over the period of the wave, 2 pi over t. It is a temporal frequency in radians per second. The new quantity is k. Notice the similarities. First of all, the numerator is 2 pi as before for the temporal frequency. The 2 pi, of course, refers to radians, but it's now radians per wavelength, radians per meter. So whereas the temporal frequency is really a per second thing, number of waves per second, if you like, number of cycles, the k is the number of cycles per wavelength. So it's, if you like, a wave crest density. Now let's look further at these variables omega and k. First question to ask is omega a scalar or a vector? Well, when we're thinking of radians and circular motion, we usually think of, when we're looking at phase, as we will later in the course, the phase of the wave, omega t. The units are dimensionless. Omega is per second times seconds. When we're looking at the equivalent in space, k, scalar or vector in 3D, we note that the operating quantity is kx. Now in one dimension, there's no question here, there's no vectorial quantities, but we're actually asking the question in 3D. So let's look at these variables t and x in 3D. T is the time. It does not depend on the spatial coordinates, x, y, or z. In 3D, however, we have the possibility that we could have either x, y, or z. So actually in 3D, k will be a vector with components kx, ky, and kz. And these components represent the spatial wave density in each of the coordinate directions. Now one might think that this is some simple abstraction cooked up to torture students, but in fact it happens all the time if we think of waves at the beach. So here's my beach, here's land, here's the water, here are some waves coming in at an angle like this, and the crests of the waves are here. So if we think of this as going from one crest to another, then the distance, these wave fronts are supposed to be parallel, is just the straight value lambda, one dimension. However, if we look at the spacing of the wave crests here, and we consider this to be the x direction, we can see that this distance here is bigger than that distance by the cosine of some angle. So this distance is this times the cosine of this interior angle, which I've scribbled as theta. So that means the lambda x here is greater than lambda in numerical value, and you can see that from the figure. Similarly, we can do a projection along the y-axis. So in fact, counting wave crests and their densities in the different coordinate directions is very important for analysis of waves. And we'll see how this comes up in our study of reflection and refraction.